My name's Hugh Abbott, and I'm looking for the best business uses of AI with the best returns. This week I spoke to JackSaunders about his machine learning project, which was used to predict when water pipes are going to burst.
In this case, it was looking at leakage in the water industry. So leakage accounts for, I think it's about 20% of water loss, and it's about £4 billion a year in water lost. So it's a massive problem for the water companies. And for this one specifically, they wanted us to try and pinpoint leakage, and they also wanted us to try and predict bursts. So what we were doing was we were looking at different areas within the network, and we had a whole bunch of different attributes that we could use to do this project. So they said we've got data on what the pipes are made of, how long the pipes are, we've got telemetry data, so sort of the changes in pressure in the network, the changes in flow in the network, and from that you can derive leakage numbers. So with the flow you can say this much we know goes on demand, this much goes somewhere else, this much is lost, so that much is leakage. And you can look at trends in that as well. So what we did for this project specifically was we took all of those features and we built a supervised learning model, and there was some sort of pre-processing to do for that as well, lots of missing data and things like that, and there's also some normalization to do as well, because one of the attributes was length of pipe. Obviously the longer a pipe is, the more likely it is to burst, because there is just more of it. You also got the age of the pipe as well, and it's often assumed that the older a pipe is, the more likely it is to fail, and that's actually not something we found in this project. We found that it was a bit of a bell curve, to be honest. The pipes that were really old, we're talking 100, 150 years old, they were pretty solid actually. They rarely burst. It was the ones that were built sort of 30, 40 years ago that you're not so sure about.
In the 70s and 80s, yeah.
Exactly. And a lot of that is probably down to survivorship bias. So the ones that were really old were just built really well, and they've survived a long time. So because they're the only examples we have of really old pipes, it makes it look like the really old pipes were the best. But actually it's just that the few that were built well have survived this long.
Or the few that built well in the easiest surroundings, the easiest soil.
Yeah, so that was something we looked at as well. We had some sort of environmental metrics on there. We had the changes in pressure, changes in temperature, changes in humidity, the rainfall, the soil fractivity, for example, so that how much the soil moves. And one of the things we found is if you have a cast iron pipe in soil that moves around a lot, it's more likely to burst than, say, a PVC pipe, which is much more pliable, can move around a little bit more.
Well, I mean, that kind of makes sense from the outside, but you actually proved it in the model.
Yeah, exactly. Yeah.
But I presume they came to you because there are too many inputs, there are too many variables for this to be put through some kind of Excel model and press a button after you write a macro. It's just too much data and too many inputs, and it really needed a machine learning model to try and make sense of it.
Yeah, absolutely. That was exactly it. There were too many things, and it was a case where they had too much data as well, and they didn't know what to do with it. You've got all of this telemetry data. They didn't know how to extract anything meaningful from that.
Meaningful knowledge,
yeah. So what you tend to find with leakage is it remains relatively flat, but with an ever so slightly upwards incline. What you get is a very slightly upwards incline, which gradually increases and increases until you get a catastrophic burst. And that's often because you end up with a sort of you have a sort of pinhole in the pipe, which as the water comes out gradually gets bigger and bigger and bigger until it reaches a tipping point where so much water comes out that the pipe just goes. So deriving some kind of meaningful features from that data and understanding how to interpret it was a big part of the project.
And can I ask you, so lots of internal data that they gathered and they couldn't make sense of. Did you go to publicly available data?
Yeah. So there's an organisation, the UKWRI, the Water Research Institute, and they maintain a database of pipe failures. So we had not only the data from the client themselves with their labels on sort of when pipes had failed and that kind of thing, but we had this curated data set that's really well maintained from, I think it's something like 18 out of 20 water companies in the UK. So an awful lot of data in there, and we were able to use that to do it as well. But we did find that there were some regional differences. So if you were to look at a water company down south compared to a water company up north, then the model didn't always translate super well. So we did find some regional differences. So we essentially just weighted the instances from the client higher than the other instances, but they were still available for context for the model.
That's interesting. And also, what did you use the geological surveys?
So the survey data was kind of supplied to us by the client. A lot of the water companies maintain their own data sets for that kind of thing.
Right.
They often get it from, DEFRA, for example, for elevation data and things like that. But then they're working with this data all the time, that they often maintain their own data set of the most useful features. So we had that from the client.
Mm-hmm. So there was a sort of data gathering process of the project, and then the next bit, I suppose, is the training.
Yeah, exactly. And one of the requirements of this was that they wanted it to be interpretable. So they wanted to understand they didn't just want an output of this pipe's going to burst. They wanted to know why. So we had to use some interpretable machine learning models, and I believe we went with random forest in the end, actually, which is always pretty robust. And from that, we were able to give them the feature importances. So we could say, for example, that soil fractivity was a good predictive factor, and combining that with the material type, then you're able to give them some good information, not just on this pipe's going to burst, go do something about it, but actually learn something from that as well that they can apply across the network.
Right. Give some insight.
Yeah, exactly.
Yeah. And in terms of time, I presume that. I don't know, but was the biggest amount of time and effort in gathering the data and cleaning the data?
Yeah, I'd say so. It was an interesting project because we had, I think it was about 12 weeks total to do it, which is a decent amount of time. But we'd done all the kind of initial data collection. We said to them, the data we got is great, but it would also be good if we could have access to some other data as well. And by that point, I think there was maybe 9 weeks left of the project, and they said, there's 9 weeks left of the project, and it's a 12-week approval process. So no, which is something you find a lot with these highly regulated industries, is they have their processes for giving you access to things, and the process often takes an awful long time.
But then you could have a version 2 of the project, which is
exactly.
Anyway, so talk us through. So the training. So you gathered the data, and then you applied. You tried to train the model, and then you needed to prove that it worked on your data that you'd already got. Yeah. And that go on. Sorry.
So that kind of proving the validation process was somewhat interesting, because we'd actually been involved in a similar project with a different client a few months prior, and that one it looked like it got really good results. And I'm one of those people that you could say glass half empty maybe. I was very pessimistic about the results. I was like, something must be wrong here, it's not going to be this good. And there was some data leakage actually, in terms of we have to split the data in a way that it's not no longer linked to the training data and the validation data, just so the model can't cheat essentially.
Mark its own homework.
Exactly. Yeah. So in this previous project, what they'd done is they hadn't split it spatially. So water companies maintain what they call DMAs, district metered areas, and they are areas of the network which can just kind of be segmented and isolated from the other areas. And what they'd done is, in their training and validation data, they'd had data from the same DMAs in both training and validation. What we did is we came in and we said, well, why don't we split that up a little bit, because you potentially got some data leakage there. And suddenly the accuracy went way down, which they weren't happy about. But it's one of those things where we're like, you have a better model now because of it. So for this project, we were very conscious of that. We were very conscious of the data leakage, and managed to avoid it in this case. And the actual validation, I can't remember the specific results, but we were on average detecting when bursts would occur 8 months before they actually did. Right. So we were able to say this pipe's going to burst. And the way we validated that was we took all of the data, I believe up to the end of 2022 for our training. And then for testing it, we applied it to all the data after that point. And when we did that, we were able to see, okay, so say, I don't know, September 2023, you had a burst occur here. We would have picked it up way back here, 8 months before. Right.
And so do you measure the model on an accuracy level? Is that how do you just state this is 97% accurate, or how do you state its validity?
Yeah, so it's with the data set. I think it tends to be about 2% of pipes that fail in the water network from the data that we had. So it's highly imbalanced data set. So if we went just with accuracy, we could have said, well, you got 98% accuracy, and it's just saying that nothing's ever going to fail. So for this one, we looked at precision, recall, and F measure for it, which it just focuses primarily on the positive class. So precision being of all of the positive instances, all the instances you've identified as being positive, how many were actually positive.
Positive failure, you mean?
Positive failure, yeah, exactly, yeah. And recall being of all of the positive instances in the data set, how many did you get? All of that's combined in a metric called F measure. So that's what we use to validate the model.
Okay. And clearly you're not telling me what F measure is because it's too complicated for me to understand, and that's not a problem. But then when they applied it, well, let's talk about how they applied it, and then the increases of, well, I hope, productivity when they applied it, and then we can also talk about the sort of cost and return. I think that would be very interesting.
Yeah, absolutely. So it's pretty useful to give some context on their process before they had access to the system, which was they literally had people manually looking at the data. 16 hours per week per area, someone was sat there just looking at the graphs for the telemetry data, and then you'd have someone in the office who's worked for the company for 30 years and says, it's probably this pipe over here, those ones always burst.
Right, so some old chap who'd been working, he had all the knowledge in his head, he just knew by staring at the data for long enough with a cup of tea and no doubt a half packet of rich tea biscuits, but he could work and pinpoint where it was going to be with a reasonable amount of accuracy, one assumes.
Yeah, these guys are, they're incredible. The knowledge that they have of the networks is incredible, but it's a problem because when those people leave, when they retire, that knowledge is gone, and that's what they had here. They had no standardized, repeatable process. So what we gave them was the output of the system was essentially a dashboard with all of the clever stuff going on in the background, and what the dashboard would return was a prioritized list of areas, and then for those areas it would pinpoint the leakage. Say it's probably these ones, and give you a kind of ranked probability of them. And by doing that, it took that 16 hours a week down to about 1 hour a week.
Right.
It was just for the processing.
But there's no way of measuring. So because this is fixing a leak before it is catastrophic. Therefore, there's no way of measuring once you've put in your system how effective it is. We think it's effective, or do they say over a long period of time we've noticed that there are less catastrophic leaks?
Yeah, so that's exactly it. They've noticed there's less over time, and it allows them to plan their maintenance more effectively. So water companies are funded in 8-year cycles called AMPs, and at the beginning of the AMP they get given a budget, and there's for different things. So they'll have a budget for pipe replacement, for example. This year is the start of a new AMP, and I know that they're planning on using the system to inform for that pipe replacement budget, which one should they go and look at because of the probability that they're going to burst in the next year, 2 years, something like that.
So and anecdotally, which often is the way ML and LLM projects get evaluated, but anecdotally, this is well trusted in the companies, in your water company client.
Yeah, absolutely. It's business critical now. It's their standard
business
approach.
Critical.
Business critical. So
That's a good set of words to use about a project that you've delivered.
Yeah, no, they're very, very happy with the results, and we're very confident in the system. And one of the other kind of key components of it was looking at prioritizing not just based on these pipes are most likely to burst, but also saying what is the cost if they do. How many people are impacted, and also what's the cost of water lost. So this particular client, they have quite disparate costs in how much water costs to get to different places. And for a sort of a standard area, it would be about £7,000 an hour when a leak is running. But they also supply some islands, and for those islands it's £70,000 per hour.
Right.
So that was a big factor in determining their where they go and actually do these interventions, where they allocate that money for the pipe replacements. Because absolutely astronomical amounts of money being lost.
Yeah. So let's talk about that. So did you do a benefits statement, a benefits analysis at the end, or did they do benefits analysis, or taking your costs and the cost of the project, the totality cost of the project compared to how much they saved? Did they do that work?
Yeah, they did. They did that internally. So they took our costs for the project, and then they basically said, so with the system, when we applied it to the data, there wasn't a single catastrophic burst that we wouldn't have picked up before it happened. But being pessimistic,
and sort of give me an idea of how many thousand miles of pipeline are you talking about?
Thousands of miles of pipeline.
I mean, do they measure it like that? Sorry, I don't know.
Yeah, they do. I wouldn't be able to give you that number though, just because I don't know, to be honest with you. But I can tell you there were 3,000 bursts a year before we implemented this system. And there wasn't a single catastrophic burst that the system wouldn't have picked up before it happened. And that's largely just down to the features we extracted from that flow data, because you can sort of see it. You know, the leakage remains relatively flat with a slight incline, and then it gets to a point where you can say, okay, it's going to reach a tipping point pretty soon. So that was a highly predictive factor, and using just that alone, you would have been able to predict catastrophic bursts before they happen. But using all the other features, you were able to predict it much earlier and also pinpoint it as well.
And so let's just go back to the benefits analysis. So they did some analysis internally.
Yeah, so they did some analysis internally where they took a pessimistic approach and said, even if we had only identified 10% of bursts beforehand, so we're talking 300 bursts, say an average duration of 3 hours per burst, then how much money would we have saved them overall? And if we're talking, say, roughly on average £7,000 at the lower end, you turn to that by 3 hours, you got £21,000. You times that by 300 pipes. Our costs were less than 50 grand for this whole project, and we were saving them. I can't do the maths in my head.
But you're the mathematician.
I know.
Just do it quick. So let's just do that. So £21,000 by 300. Let's get the number. And this is per annum.
It's only £6.3 million.
So you think they were saving, at a conservative estimate, £6.3 million, and your costs were 50. Let's say 50 grand. Their costs were let's say another 50 grand. So 100,000 for the project, and they're saving £6.3 million. Yeah, it's
wild.
I love it.
For such a simple project as well, using, as we were saying, the simple side of machine learning. The traditional supervised learning rather than anything fancy.
And did you? Well, I hope you've managed to sell this to every water company in the UK.
Yeah. We're doing our best.
Well, that's a great. I mean, that is an amazing return.
Yeah,
brilliant.
absolutely.
I love that. I am looking for great uses of artificial intelligence, and that I'm going to say is a fantastic use of artificial intelligence. So well done, you. Congratulations.
Thank you.